Okay, so maybe let us begin. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. We have two talks today. The first one is by Ricardo Ferreira from Coimbra, Portugal, and he's going to talk about domain wall networks, signatures in gravitational waves, primordial black holes, and cosmic birefringence.
Can I start?
Yes, please.
Yeah. Hi everyone. So let me first thank the Anish and the organizers for putting this together, for allowing me to present some recent works on the subject. So my goal for today is to talk about domain wall networks, and in particular some phenomenological signatures that they may have in terms of gravitational waves, primordial black holes, and cosmic birefringence. So the work is most of what I will say is related to two papers from this year, with Silvia Gasparotto, Takashi Hiramatsu, Ipei Obata, and Oriol Pujolas, one of them, and the other also with Alessio Nuttari and Fabrizio Ropineve. And this are the last two of a sequence of papers where we have been discussing this topic. So let me go step by step and try to put you in context first of what are domain walls. But before even going to the domain walls, let me give a one slide motivation to put things in context to me. So, basically, the way I see this study of domain walls is that I'm here in Portugal, and there are several possible routes for new physics that we are all exploring, I imagine. We don't know where the new physics is, so we try different possibilities. And the domain walls, they appear something that can appear along the way. So along the way to some new physics with your own, depending on your bias. There can be along this path some monsters, and these monsters are for me the domain walls. So these cosmological objects of a cosmological size that in themselves they are not the microphysics that we are looking for. So they are not the end of the road, but they are extremely useful, because if we do find them, if they are really loud, they can serve as a lighthouse that will guide us in this path for new physics. So they are indispensable. In particular, in this case, this is my own bias. The new physics that they could hint for are, for example, axions or Majorans, or other beyond standard model scenarios where these beasts can appear. Okay, so now let's go to something less philosophical. So this is the outline of what I would like to tell you today. So I'll try to start by the basics of domain walls. So how do they form, and how do they reach the scaling regime? And then I will have two parts about our observational signatures. First, in terms of gravitational waves, and some interesting connections to pulsar timing arrays, the data from pulsar timing arrays. Primordial black hole formation is a side effect of this. And then in the second part, the possible connections between the existence of domain wall networks and some evidence for cosmic birefringence that has been recently found in the CMB data. So let's get started then. So what are these domain walls and what do they form? So domain walls, as I mentioned before, so they come in many models, and they are basically the result of the spontaneous breaking of a discrete symmetry. So the pointer is not working, but basically if you have a discrete symmetry, when it is spontaneously broken in different parts of the universe, you will either fall on the minima on the left or on the right, because they are either equal or nearly degenerate. So in one place you find in the black, and the others you find in the red. This is just the rephrasing of the Kibble mechanism. And of course, in between the black and the red, I mean, the field is continuous. So in between the black and the red, the field needs to go above the wall. So it needs to go above the potential wall. And that's basically the domain wall configuration. So it's the field configuration that connects the two minima. So this is from the point of view of the potential, from the point of view of the field, in real space. Basically, is the figure on at the bottom. So you go from the black minima to the red minima in some length scale. And this length scale is one of the main characteristics of the domain walls, which is what we call the domain wall width, which is roughly proportional to 1 over the mass of the scalar field that composes the wall. Another relevant parameter to characterize the walls is how much energy do they store, and that's characterized by the tension, which is the energy per surface, energy per unit area. So these walls can be approximated to I mean, we will work in the thin one limit, so they are very thin compared to cosmological scales, and therefore they are basically two-dimensional objects, and where we can define this tension, and this tension is related again to the mass of the field and to the distance between the minima squared. Okay. So what I've described you is one wall, but we'll be interested in a full network, not just one wall. And of course, what I mentioned, that one wall corresponds to the connection between two minima, but this will happen everywhere in the universe. So everywhere there will be these walls here and there, and they will be connected, and that's what forms the network. So the network is the union of all these walls. And I have here an animation from a simulation by Takashi Hiramatsu, and let me play it. So basically, what you can see that, let me try to stop in the beginning. So in the beginning, there is no symmetry breaking. So the field is a mass, is around zero, doesn't choose any particular minimum. And then the symmetry breaking happens, and you see the walls, these this structure of long walls forming. They still radiate some leftovers of the initial conditions until they kind of freeze at the end of the simulation, and you end up with this type of things. So the dynamics that I'm showing here can be described as following. So on large scales, so when the walls have curvatures much bigger than the horizon, they are frozen by Hubble friction. So Hubble friction freezes them. On the other hand, on small scales, so when the curvatures of the wall are become subhorizon, the domain wall tension will dominate over the Hubble friction, and main walls they basically start to accelerate, and then they dissipate in different ways. Either they collide against each other, or they chop, or they intersect. So there are several dissipation channels. Now, these two ingredients together on large scales and on small scales is what allows to reach the so-called attractor solution, the scaling regime. So the scaling regime is the result of all this process, and it's basically in the when the network reaches the scaling regime, it basically can be characterized by roughly one wall per Hubble patch, with a typical curvature of 1 over h. So that's basically how does the network looks like in the scaling regime. Okay, so we ended up with these many walls, this network, but as you have heard probably these big words, there is something called the domain wall problem, which had been pointed out long ago by Zeldovich already in the 70s. And And the domain wall problem is the simple fact that if you compute the energy density of this domain wall network, so meaning, so basically we have a tension, and then you put the typical radius of the walls, as I said before, in the scaling regime is 1/h. So the energy density of the network is roughly sigma times h. And as you can see, it goes like 1/h. So it redshifts very slowly. And as time goes on, it will dominate the universe, the energy density of the universe, and become incompatible with observations. So this is the main problem. And it still, of course, remains true. Now there are at least two caveats that can circumvent this conclusion, and which are the following. So first, that the domain walls annihilate, so that they don't live forever. And so normally the network is, okay, at least this one where there are no hybrid, it's not an hybrid network where there are strings and so on. So it's just a domain wall one. It's stable. And therefore, we want to annihilate it, we need to put a further ingredients. And one ingredient is, for example, that the symmetry is not exact. So the discrete symmetry is only approximate. And if the symmetry is approximate, as you can see in this figure, if there is a gap in the vacuum energy of the two minima, a gap delta V, at some point this gap, even if small, even if it's very small, at some point it will create pressure. And when the energy density, basically when the energy density in this, the what's called the bias energy, the gap in energy densities is comparable to the energy density in the wall, so sigma times h, then the network will annihilate. So this defines the annihilation time of the network. There are other ways to annihilate the network, but this is just one example that I will use then afterwards. So I'll consider then this case number one in the when discussing the gravitational waves. The second possibility to avoid the domain wall problem is that the tension is small enough, or very small, so that the walls didn't have yet time to dominate the universe, and therefore that everything is still compatible with observations. And in particular, that means that the tension of the wall needs to be smaller than MEV-Q. And I'll be mostly in this regime when discussing the cosmic birefringence phenomenology. Okay, so this is, with this I end the basics of the domain walls. So now let me go to the phenomenological parts, the gravitational waves. So I'm now working on caveat number one. So to avoid the domain wall problem, the walls annihilate. Now this annihilation of the network, of course, as you can imagine, that it leads to gravitational waves. Now, compared to other defects, the nice thing about the domain walls is that because they have this tendency to dominate the energy density, it makes them kind of a natural source. They are not natural source of relics, so they are naturally loud relics of the early universe. Because if they are there and if they live for long enough, they will unavoidably be quite important. And what has been found, well, mostly using numerical simulations of the domain wall networks, is that, well, there are some, you can also do some analytical estimations, and the numbers work out nicely. So they are kind of in good agreement. Is that the spectrum of gravitational waves has the following form, roughly. So is of order 10 to minus 10, and I will tell you in a second why I choose 10 to minus 10, times the energy density in the domain wall network at the time of annihilation, here normalized by 1%. This quantity square times a spectral function. So this is how the gravitational wave spectrum looks like. So where this spectral function has the following shape. You can see on the right, it peaks at the Hubble at the time where the network annihilates. then redshifted to today. On large scales, it goes as frequency cube, and that kind of residual of the causality arguments. And on the large scales, sub-horizon, it goes like 1 over f, so 1 over frequency. Now, the reason why I singled out this 10 to minus 10, so basically, is to say that the goal was to say that if the network is around 1% of the total energy density of the universe, when it annihilates, the gravitational wave signal is in the ballpark of the current gravitational wave detectors. So basically LIGO and PTAs. And so this is a general statement. Then of course, whether the peak frequency is on the right frequency band will depend on the annihilation temperature.
Hello.
Yes.
Yeah, may I ask a question?
Yeah, of course.
Yeah, here the gravitational wave you have computed like when the domain wall doesn't dominate the universe. So what will happen like if this domain wall is kind of metastable, but at some point like it start dominating the universe before its annihilation?
So the case where the domain walls dominate the universe is normally seen as problematic because it's hard to get out of it. So I don't
domain
think
wall
so.
will eventually decay, right? You say like at a time, like when Hubble parameter is of like del V divided by its
yes,
tension.
but that's true. But in doing this, because this quantity is decreasing in time, sorry, sigma times h. So I don't have the pointer. But if you look at the right-hand side, sigma times h is decreasing in time, and delta V, no, delta V is constant. So if you wait for long enough, you will annihilate. Now, if the domain walls dominate, the Hubble will not decrease, will decrease very slowly, because the domain walls are like dark energy, like so it's
yeah.
So it will be harder to get out of it. I have a question.
Okay.
Yeah.
Thank you.
I see a hand. Yes, please.
Ricardo, hi. Very, very interesting what you're talking. But there is another option, right? I just wanted to make a comment. There is another option to avoid the trouble with domain walls. Namely, the domain walls may just melt down and go away.
Yeah, I agree.
That requires time-dependent or whatever, temperature-dependent tension, but that's quite natural to have.
Yeah, I agree. Thanks for mentioning. So
yeah,
there are other ways apart from this one. You can have symmetry restoration, which I think goes on that direction. Tension, time-dependent tension. So yeah.
Yes.
Thanks.
Yes. And another thing, what I wanted to ask you, because on this plot of omega for gravitational waves, you have spectral index in UV, which is f-1. But I'm not sure. There were other simulations where it was minus 1.7, and what we have done recently, it was I think minus 1. Something like 3. Yeah, 1.5,
Yeah,
1.3, depending on initial conditions.
It's a good question. So, so in the literature, there's been, well, until recently, mostly 1 over f. But what I can say there so we also have some work where we found a different slope.
Yeah.
Although in that work we were working in matter domination, so it was slightly, so that's slightly different. However, what we noticed, which I think is general in the simulation, is that the simulations tend to develop a UV peak at high frequencies. Most of them.
But,
and this UV
but
peak,
it's pathological. It's
which is pathological, but
yeah,
it's completely pathological, but it has an effect, a strong effect on the slope. So if you try to extract the slope, this pathology is making an artificial change in the slope. So you can change the slope from -1 to minus 1.2, perhaps minus 1.3. So I think some other studies have said, I mean, so in general, it's roughly compatible with -1. Now, if it's exactly -1, I agree with you that needs to be shown more precisely, if it's precisely -1 or perhaps -1 point something.
Yeah. I just want to say that exactly we observed this pathological peak. We killed it. We killed the effect of this peak. And after killing it, we still see this different slope. And that's where we see that already, you know, there is no change. I mean, basically this peak is erased and it's still not the same. But am I right? There are no theoretical arguments in favor of exactly f-1, contrary to f cube.
Yeah, I'm not. Good that you mentioned it. Yeah, it would be nice to have a better analytical understanding of the 1/f. I mean, in the first order phase transition literature, the 1/f comes out in this envelope approximation.
So there is an argument. Okay.
So there are in something closely related but not exactly the same. There are arguments for the 1/f. So. That's why the 1/f was also never strange, I think.
Okay.
But I agree that it needs to be. It's something to really investigate to kind of nail down what's the precise number. Yeah.
Great.
It could also depend a bit on the details of the
initial conditions, for example.
Yeah, and also of the network. If you have hybrid networks, could change a bit. The domain wall number, perhaps. So yeah, but something definitely super interesting to look at. Yeah.
Great. Sorry for distracting you.
No,
but thanks.
No, thanks. Yeah, please ask me questions. So yeah, I'm very willing to discuss. Yeah. So got the now. So coming back to on track. So I was just arguing that. Yeah, so if you have 1% of the domain wall network in of the energy density of the universe in the domain wall network at annihilation, you are in the ballpark of the gravitational wave detectors. And on this regard, let me highlight the work we have done this year. What we have shown is that, so we compute a gravitational wave throughout annihilation, which was not done before. They were gravitational waves were computed during scaling, during the same regime. So we extended so we did our own simulations and we extended throughout the annihilation. And what we found is that gravitational wave emission lasts for longer. So a factor of 2 longer, basically, than previously thought. And this has a large impact because the amount of the abundance in gravitational waves goes like eta to the 4. So a factor of 2 can give a factor of 10 and gives a factor of 10 enhancement in the final result. So the conclusion is that for the same microphysical parameters, so meaning what mass of the field, tension of the wall, you'll get 10 times more gravitational waves than what was previously thought. Okay, now this was a general remarks. Now let's go a bit more to data, and what's interesting in this regard is that so you probably have heard about these pulsar timing arrays, observatories. So they found evidence for a stochastic gravitational wave background. So this was news from last year. The signal is, so let's say the vanilla interpretation of this data is in terms of supermassive black hole binaries. So that's kind of the vanilla interpretation. However, even there are still holes in the understanding, because the spectral slope that you would expect from the black hole binaries does not exactly match what they are finding. And this might be connected to what is called the final parsec problem, which is the fact that, well, with still minimal assumptions on how the supermassive black holes binaries merge, it seems to take a time longer than the age of the universe for the merging to occur. So I mean, we know that they merge, but we don't understand the dynamics that makes them merge in a time smaller than the age of the universe. And of course, that would affect the spectrum. So there are holes in this understanding. So therefore, I mean, I think there is plenty of space to consider new physics options to explain this signal. And in fact, that's what we did even before the last year paper. So in 2022, there was already some evidence in the pulsar timing arrays for a signal. It was not clear whether it was gravitational waves at that time, but there was already some signal. And what we have shown was that if that signal was in 2022, we showed that if that signal was really gravitational waves, they would be could be explained by domain wall networks that have a tension of around hundreds of TeV cube that annihilate around 100 MeV temperatures. And this is very suggestive because, of course, these are the temperatures around the QCD phase transition, and therefore it suggests that QCD could have a role in annihilating the network. So perhaps it's the one causing the symmetry, causing that the symmetry is not exact. I mean, so QCD effects could cause the annihilation of the network, and we already mentioned that in that paper. Now, what was interesting that then, after the signal became more, it was become clear that the signal was made of gravitational waves. So in the last year data, Nanograv did an analysis and compared the different models to the standard vanilla interpretation of supermassive black hole binaries. And what they found was that the domain wall interpretation can be up to, there are two cases, but in one of them it can be 20 times better in terms of bias factor than the vanilla interpretation. So in meaning, I mean, this does not show that domain walls are the answer, of course, and that, as you can see, there are other models and some of them also perform well, but it shows that the domain walls really are a good, can explain very nicely the data. Furthermore, one nice thing about these walls that they don't come in isolation. I mean, you have a lot of energy in the walls that the walls annihilate, but this energy, where does it go? And what we studied also already in this paper of 2022 was that there will be also a significant amount of either dark radiation or collider signatures. Because either you decay to a dark sector and it needs to be a radiation, some kind of dark photon, or you need to couple strongly to the standard model and decay into the standard model. So and these two options have two different phenomenology, but it can be tested. And the third possibility is that you form primordial black holes as a side effect of the collapse. And so let me tell you more about this. This is the work we have done this year. So what's the story? So before annihilation, you saw the movie. So you have these Hubble-sized domains, and each one will choose a different vacuum. And there will be each vacuum will be equally distributed. So here, for simplicity, let me consider the Z2 symmetry. So, and in this network, having a large pocket, so a pocket which is all in the same vacuum, is very rare because the most common thing is to have Hubble-sized structures. So here I denote by the blue and the green. So these are two minimums in a Z2 symmetric potential. And in one Hubble, you are in the blue and the other are in the red, in the green, and so on. Now, after annihilation, what happens is that everything which was subhorizon goes away, and only the very big structures survive, the ones which have the radius bigger than 1/Hubble. So this is the leftovers of the network are these rare false vacuum pockets. And what we did was to estimate this the probability that you have such a pocket in the following way. So the probability, let's consider a big pocket that is in the blue minima. So each Hubble size domain has a probability 1/2 of being blue, 1/2 of being green. So if it's 1/2 of being blue, and if you have n Hubble patches, the probability to find such a pocket, such a closed domain wall, is 1/2 to the power n. And so that's what I show in the equation below. So the probability to have a false vacuum pocket with a radius RDW is basically 2 to the power the ratio of volumes between the pocket and the Hubble at annihilation. So basically, how many Hubble pockets fit inside the wall. Now, then of course these pockets will have some dynamics, and we study that by solving the number-Goto equations that feed in the time evolution of the radius of the domain wall, and we end up finding what we call the false vacuum fraction. So false vacuum fraction is the fraction of space that is still in the false vacuum. So this counts the number of walls that are in the number of closed domain walls, and we find that it goes like 2 to the power minus 1.8. This is just a number, but note that it goes like eta cube. So it goes basically very fast, super exponentially to 0. So previous works argue that it goes like power law, but what we argue in this paper and what we find is that the false vacuum fraction decays very, very fast. So these bubbles are rare and they go away very fast. However, even if it's very fast, by the way, we find that the analytics kind of reasonably match the numerics. So this you can see the orange and the blue curves here. So we have some, it's not just a analytical estimation, we also had some cross-check with the numerics. Now, okay, so far I just mentioned, I said the word false vacuum pockets a few times, but the side effect of the presence of these pockets is the following. The bigger they are, the rarer they are. But they store an energy inside, which is delta V. And this delta V does not dilute, it's vacuum energy. Now, at some point, because the background energy is decreasing, at some point, the delta V becomes equal to the energy density of the background. So, so the energy, basically, that's the point at which you have an overdensity of order 1, basically. And what you can compute, what you find is that if you compute the Schwarzschild radius of a bubble with this vacuum energy and a radius of order 1/h, the Schwarzschild radius is 1/h as well. So when the false vacuum pocket enters the horizon, it's already inside its own Schwarzschild radius. So this is a black hole. So this is automatically a black hole. So, and this is the main formation mechanism. Now, there is another possible population of primordial black holes. So, because even the bubbles that enter before this condition is met, the condition delta V equal 3h squared mp squared, the false vacuum pockets could enter the horizon, and if they are able to quickly collapse without losing energy, they would also form black holes with different masses. However, this other population is harder to estimate because, okay, these pockets are not spherical, and so they will spin, they will radiate scalar field, they radiate gravitational waves, and therefore they lose mass. And because they lose mass, then it's not clear if they really enter their Schwarzschild radius at some point. So this needs to be studied numerically. Okay, but now we have this. So as a side effect of the network annihilation, we have these black holes, and we have a probability for them to form. By the way, I didn't say the mass, but the mass, it's easy to find. It basically, the mass comes from the, you can compute the mass inside the bubble by it's basically delta V times the volume of the bubble. So that sets the mass of the black hole that you formed. Okay, so this is the outcome of this story, is that if we put together gravitational waves and primordial black holes. So let me try to guide you through this plot. Basically, this plot is alpha gravitational wave, and alpha is the fraction of energy density in the domain walls at the time of gravitational wave emission versus the temperature at which this happens. So these are, you can trade this parameter by your microphysical parameters. So you can trade alpha and T by sigma and the symmetry breaking. So there's a one-to-one connection. And the colors are the regions that can be probed by different gravitational wave detectors. SKA, LISA, LIGO already puts constraints, LIGO Virgo, Einstein telescope, etc. Now, let me start from the left. The red contour is the region of parameter space where you'd explain nicely the nanograv 15 years data. So it's the 1 and 2 sigma contours. So basically, this you would need to have basically 10% of the energy density of the universe in well, it can be a bit less, but yeah, around 10% of the energy density in these walls, and annihilation temperatures around the 100 MeV, as I mentioned before. Now, one interesting thing to note, and this is what the dotted black denotes, is that if you compute the mass of the black holes that are formed as a side effect of explaining nanograv, you'll find that the mass is around the solar mass. And basically these two lines denote masses between 1 solar mass and 100 solar mass. Now, we don't know exactly how many, that there is some big estimation, big uncertainty in the abundance of these primordial black holes, because the number that goes in the exponent is very sensitive to it. Yeah, so there is a chance that we could have correlated solar mass black holes with this nanograv signal. Another region which is very interesting is the one inside the green area. So let me say the blue is the constraint already from primordial black holes. So meaning that if you are above the thick blue line, you produce too many black holes from the mechanism, and you are already excluded because of the constraints on primordial black holes. So above the blue is excluded by that. However, inside the green area, this corresponds to the asteroid mass range, where the black holes would have asteroid mass range. So if you are on the thick blue line, and in this mass, and you have these parameters, so if you annihilate, in this case, corresponds to annihilation temperatures between 10 to the 6 and 10 to the 8 point something JeVs, you could have a dark matter made of primordial black holes in this way, as I explained. Yeah, so there are different, there are interesting consequences that these black holes can have. And furthermore, let me say that, as you can see, the blue line is on top of the LIGO Virgo Cagra sensitivity bands. So, so the gravitational waves, so in case that we have primordial black hole dark matter from this mechanism, the gravitational waves associated from the annihilation of the walls would be on the frequency range of LIGO, and if not LIGO, they definitely would be inside Einstein telescope. So we could really probe this possibility nicely. Okay, now I'm a bit out of time. I I wanted to change gears to this second part. I don't know if can I have 5 more minutes?
We have 7 minutes.
7 minutes. Okay. Okay. Let's move a bit to gears then. So I'll still keep on the domain wall networks. I just now explore a different range of parameters. And this time I will start by starting from the data instead of from the theory. So what is the data saying? So there's been in the last few years a few recent analysis of the CMB data, and what they found is that the CEB correlator. So the CEB correlator is a correlator that if it's non-zero, it means that there is some parity violating effect. And this recent analysis led mostly by Eiichiro Komatsu and Minami and others, what they've shown is that there seems to be a non-zero signal, which you can translate it to what's called an isotropic birefringence. So isotropic birefringence means that the polarization axis of the CMB photons has been rotated by this amount, beta of order 0.34 degrees. In particular, the null hypothesis has been excluded at 3.6 sigma, so it seems to be quite interesting. There is still some discussion about potential miscalibration, systematics, because the Planck satellite was not really dedicated to make such a measurement. So there are still some caution to have, but with new data, in particular from Atacama Cosmology Telescope, we'll probably have independent probes of this, so keep tuned. Now, so this is the data part. Now, on the theory side, I think is super nice because there is no obvious astrophysical late time explanation for this signal. So, okay, while for the gravitational waves, there is a vanilla scenario. Here, there is not really a vanilla scenario. We don't expect to observe anything there. So it's kind of a clean case for new physics. In particular, the main ingredients to explain it are also very simple. So you need a parity violating coupling to photons. And I'm already putting a axion-like coupling to photons, phi FF2. And on top of that, you need a larger field excursion. So meaning that the amount of birefringence is basically proportional to the integral over the line of sight from recombination to today of phi over f. So of the velocity of phi over f. So what matters is how much the field has varied from recombination to today. And as I hinted, and as you can understand, these ingredients immediately call for an axion, right? And this is not surprising, and it has been explored already. In particular, the idea that an ultralight axion causes birefringence is already quite old, and in this context, so in light of this new data, it has also been explored. So there is some ideas of making some dark energy or dark matter-like axion that is kind of populating a condensate and is creating this birefringence in the CMB. And the second idea that people have explored, that this includes ourselves, is that axionic defects are the cause of the signal. And by axionic defects here, I mean domain walls, but not only, also cosmic strings. So what's the trick here? So the domain walls are made of the scalar field, right? Are made of this axion phi. And when a photon crosses a wall, if there is a coupling to photons, it will see its polarization axis rotated by this beta equal to 0.1. Then there is a order 1 parameter, never mind, times delta phi over f over 2 pi degrees. So So you see that if delta phi over f is of order 2 pi, you have a signal of 0.21, which is basically very much on the ballpark what has been observed. Now if you think about the walls, and now look at the plot on the right. So the walls are precisely such a case. So if a photon crosses the wall, it will see a delta phi of 2 pi over f. So it's the difference between minima. So the f's cancel out in the computation of beta, and you have a signal which is very clean and to some degree model independent of 0.21 C gamma, which is, I think, very nice. So the fact that the f's cancel out, I think, is very peculiar of the axion case. And in particular, the signal is also independent of the main wall tension. So even if the walls are very weak, the tension is low, it doesn't matter. What matters is really the field excursion. Now, this was one wall. Of course, we don't observe one wall. There are many. So if we have a network, the network is composed of many walls. So this is what this is an illustration of what happens. So look at the left, and here it's what I call idealized Z2 model. So we are in the center of the circle, and the edge of the circle represents recombination. So at recombination, the network is in scaling. So if it's in scaling, and the scaling, so both minima are populated equally, and both minima here I denote by blue and red. And you see that the number of blue and red area, the area in blue and area in red is roughly the same at recombination. Okay, now the photons propagate. They will cross some walls depending on the direction they take, and we live at the center. But at the center, we either live on the blue or on the red. There is no third option. I mean, we kind of broke. We locally broke the symmetry. So we need to. We live in one of them, and this creates automatically an asymmetry in the problem. And therefore, if we live on red, it means that at least half of the photons had to jump one wall from blue to red. So then when you average over the sky, you will have some isotropic signal. So there is an isotropic effect because of this. And this is what I show below. So the isotropic beta is basically the same expression as I had in the slide before, but now a bit more refined. So it's 0.21 times the average of phi over f at recombination minus the value it has locally. So where we are now. And you can see on the right, this is what we did the same we took a snapshot from the simulation, a two-dimensional cut, just to illustrate that the simulation has very roughly the same feature. So at the edge, so I'm looking at the circle on the right. At the edge, it's the amount of red and blue is similar, and then at the center we are at some specific position. Okay, I'm getting a bit out of time, so let me just say quickly a few words. The network, what is nice about this network is that to explain the birefringence signal, the isotropic birefringence signal, the network will cause other effects. So there will be anisotropies. So the amount of birefringence is of course angle dependent, and we have computed that what's the amount of angle dependence. So there will be a L dependence in the signal. What's nice is that we could in principle probe the time of formation and annihilation of the network, because depending on if the network forms or annihilates between recombination and today, it will induce some time dependence in the birefringes that can be in principle probed. And third is that for this birefringence signal, the main wall tension is not important. However, if the tension is large, you will also have gravitational waves, just as the same as the one that I mentioned before. But these gravitational waves will be at CMB scales. And in fact, we derived constraints. I think these were the first constraints on this range of parameters, where on the tension of the wall versus the annihilation temperature of the network, So you see there is normally the MEV bound so domain wall networks needs to be below MEV if they live until today, and we improve slightly on that. But if they annihilate between recombination and today, they can be a bit more energetic, so they can go up to 100 MeV. So tension to the power 1/3. Okay, and my last slide, and then I go to the conclusion. So you may wonder about cosmic strings, because I've just talked about walls. In the case of cosmic strings, so if the walls are attached to cosmic strings, as it happens in many cases in axion physics, not always, but in many cases, the situation is a bit different because the strings provide kind of an axis of symmetry. So photons that come from one side of the string or from the other will see different opposite field excursions with opposite signs, and there is kind of a washout effect of the birefringence. And this has been discussed in previous work. So what we argue now is that it's true, but if the network lives until today, there will be a remnant of the network, either a wall or a string loop. Here on the right, here I denote this is a wall cutting our present sky, let's say. And if the network lives until today, there will be a defect at most at redshift around 1, right? Because there is basically 1 defect per Hubble patch. And if this defect is there, this will cause, again, an isotropic birefringence, because all the photons that come from the direction of the defect will be rotated. And the ones that do not come from the defect will average out. So in the end, you have an effect which is proportional to the solid angle that the defect covers in the sky. So you see the equation 0.21 times omega over 4 pi. And what we find is that if the defect is at redshift 0.45, which is not so crazy, you could still explain the birefringence signal. So we are still working on that, but so I think it's nice to see that even the string wall case works out for birefringence. And I conclude here. So I already took a bit more of time, so I will leave the conclusions for you to read. Thank you.
Okay, so thank you for the nice talk and many detailed analysis of domain walls and other signatures. Anybody in the audience has any